Yes, so welcome to the group theory video lecture 12. So in the last lecture, 11th lecture, what we have discussed uh, was automorphisms and a subclass of automorphism called inner automorphism, and we proved that for any group G, uh, G quotient, the center Z, it is isomorphic to the inner automorphism using the first isomorphism theorem. So in this lecture now we are going to discuss the property of an automorphism, very special property, which is very useful in problem solving, especially group theory problems which are asked in net exam. So this is the lemma. We have already discussed this in Google Meet, but for this completeness of the video lecture series, let me also do it here. So let G be a group, and phi is any automorphism of G. So phi belongs to odd G. This is A script AG, which is the set of what? Group of all automorphisms. So if A is an element of G, if A belongs to G with order of A is greater than 0. Order of A is greater than 0, that means order of A is a finite number. If order of A is 0, then A is an element of infinite order. So here A has finite order. Then uh, whatever the order of A, the same is the order of phi. So order of image of A, that is order of phi A, is same as order of A. This is the result. And this is very much useful in finding the number of automorphisms of a cyclic group. So we are going to first prove this and then consider two examples based on this result. So suppose order of A is n. Suppose order of A equals to n for some n belongs to n. So that means order of A is greater than 0. So A is an element of finite order. That is, what do we mean by this? That is, A raised to n is identity, and n is the smallest such integer. Actually, I should write n is the smallest integer such that A raised to n is identity. But yes, so I'm writing like this. So n is the smallest such integer. Now, what we have to show, our claim is to show that. So we claim that order of phi of A is also n. Order of phi of A is also n. So to show that order of phi of A is n, we have to show two things. First, phi of A power n, that is identity, and second, n is the smallest. So first, let us compute what is phi of A power n. So phi of A power n. This is actually nothing but we write like this. This is phi of A power n. It's the same thing, right? We are not just writing the brackets. So that means this is phi of A, phi of A, phi of A. How many times? It's n times. So this is like this. It is n times. So because phi is homomorphism, this is nothing but phi A. How many times? So A appears n times. The reason is since phi is a homomorphism. Right? So phi is homomorphism. So this is A n times. And this is what? Phi of A power n. But order of A is n. So phi of A power n is identity. So this is phi of E. Since A power n is identity and phi of E is, again, this is identity. So phi of A power n is identity. This is what we have shown. And now we show that n is the smallest. So suppose there is suppose phi of A power k. This is identity for some k less than n. for some k less than n. Suppose this happens, then that means phi of a power k is identity. That means again as above, phi of, because phi is homomorphism, then so phi of a power k is identity, which is nothing but phi of e, because phi is homomorphism, so phi of e is e. And so we have phi of a power k is same as phi of e, and since phi is 1 1, not on 2, so since phi is 1 1, a power k is identity, right? Phi of x equals to phi of y implies x equals to y, so a power k equals to identity. So this is what we have, which is a contradiction. This is a contradiction for why? This is because order of a, first of all, this is a contradiction because order of a is n and k is less than n, so this is not possible. A power k is identity, order of a n is the smallest such integer, so this is contradiction and hence the claim. So our claim is correct. So that means order of phi of a is also n. So if it is an automorphism, then the order of an image and order of an element, they are same, provided the order of element is finite, it's greater than 0. So now we determine the automorphisms of a cyclic group. So the first example, in fact both examples we are determining automorphism of a cyclic group, but first time we consider, in the first example we consider finite cyclic group. So determine automorphisms of a finite cyclic group. Right, so let G be a cyclic group of order R, and G equals to A. So that is, G is this cyclic group generated by A, so A square, A cube, and so on. How much? Up to A power R minus 1. A power R is and what is order of A? So order of A power R is identity. So order of A is, because G is generated by A, so that is the same thing. So order of A is also identity. Okay, sorry, order of A is also R. So that means A power R is identity. Okay, now suppose phi is automorphism. Suppose T is an automorphism. Then what we are actually saying is that we do not need to know T for all these elements. If we know the value of T at only just one element A, only this is enough. Why this is enough? That is the explanation which I am writing here. So suppose let T belongs to OR G. So T belongs to OR G. Then what we are saying? So it is sufficient to determine the value of T at A. Why it is sufficient? Because T is homomorphism and G is cyclic. So if G belongs to G, G is any element, then it is one of this element. So one of this element, then G equals to A power I. So this is A power I for some I, right? And T, since T is homomorphism, so because T is homomorphism, so what is T of G? T of G equals to T of A power I. and because it is homomorphism, this is nothing but T of A. So I times, which is T of A, T of A, T of A, T of A. So this is T of A power I. So that means we need to know T of G. To know T of G, we need to know only this much, T of A, because G is A power I. So T of G is nothing but T of A power I. So if we know G, we can find out. If we know T of A, then we can find out any T of G. So that is the remark that for cyclic group, to determine homomorphism, we need to just determine only one image of only one element, and that is the generator. Any generator, if we know for cyclic group the value at generator, then one can determine uh, the value at every other element. So we need to find out T of A. But what is T of A? T of A, actually it's an element of G, which is the cyclic group generated by A. So then T of A is a power of A, because it is in G, so it's a power of A. So then suppose this is A power T for some T. So that is also A power T, one of this element. T of A also will be in G, so it is one of this element. So it is A power T, suppose. Now what we claim is, uh, if T is an automorphism, then this T can only have so many values. So this T will be uh, co-prime to the order of group. So this T will be co-prime to R. This is what our claim is. And converse also is true. So we claim that GCD of T and R equals to 1. So suppose GCD of T and R equals to D. Let us say it is D. We show that D equals to 1. Yes, one more thing, because T is automorphism, what is order of T? So also here we can write also order of T of A. This is same as order of A, and order of A is the generator of the cyclic group of order R, so order of A is R, because this is automorphism by previous lemma, right? So this is nothing but it is by previous lemma. So this lemma, order of an element, is same as its automorphic image. So by that lemma, order of T of A is also R. But now, if suppose the GCD of T and R is D, then what is T of A power R by D? T of A power R by D. What is T of A? T of A is, we have taken A power T. So this is A power T power R by D. So if GCD is D, then what we can say, then D divides T and D divides R. That means R by D is an integer and T by D is also an integer. So this means this is A power R and T by D. So no worries. T by D is an integer because D divides T. So this is A power R and T by D. And what is A power R? Order of A is R. So A power R is identity. E power T by D. T by D is an integer. So this is E. So now what we have is order of T of A is R, and T of A power this guy equals to identity. That means the order must divide this power. And this is the exercise which we have already seen earlier. If order of A is n and A power k is identity, then n must divide that k. So order divides this power. So what we are going to deduce from this is, since order of T of A equals to R, R divides R by D, and R by D is smaller if D is greater than 1. So R divides R. So this is only possible when D equals to 1. Otherwise this is not possible. So this is possible when D equals to 1. So that means GCD is this T of R, T and R, GCD is 1. This is the thing. When T is an automorphism, G is a cyclic group of order R. And conversely, Conversely, suppose GCD of T and R is 1. Conversely, suppose this is 1, then we can easily prove that then T from G to G defined by T of A equals to A power T. So order of G is R, and what we take is T of A equals to A power T, then this is an automorphism. This is an automorphism of G. So conversely also this is true. So conversely, if GCD is this one, then that is T belongs to odd G. So when T belongs to odd G, GCD is 1, and conversely uh, when GCD is 1, T belongs to odd G. So this part, converse part, I leave as exercise. Homomorphism is very easy. 1 1. Onto is easy, right? So for 1 1, you have to use the property of GCD. You have to use somewhere the fact that GCD of T and R is 1. This is given to us now. So the hint is for 1 1, use the fact that if the GCD of A and B is 1, then there exist integers x and y such that ax plus by equals to 1. Using that fact, show that this is, or any other idea if you have any other proof, whatever you feel is good, whatever works for you. So this is that means how many automorphisms are there for a finite cyclic group of order R. For example, if I consider G equals to, let us say, the cyclic group generated by I. So this is what? This is 1, 1, minus 1, I, minus I. Right? So this is the cyclic group generated by I. And so how many automorphisms are there? So now this is if and only if, not just if. So you have T going cyclic group. So T of A equals to A power T is automorphism if and only if T and R are coprime. So the number of automorphism is nothing but what is the cardinality of odd G? So cardinality of AG. In the cardinality of AG, this is same as cardinality of odd G, and this is just another notation. So in this case, it will be so A going to A power R. Here R is 4. A power T. A going to A power T is automorphism if and only if GCD of T and R, this is 1. So R here, R is 4. So T and 4 is 1. So this is automorphism. So how many such will be there? Which is nothing but phi of 4. Euler's function phi of 4. That is the number of integers which are less than 4, coprime to 4. So 1 and 3. So this is number is 2. So there are only 2 automorphisms. As you can see, one can list the automorphism. So T from G to G, T of x equals to x power T, where T equals to 1 and 3 will be, so then T is an automorphism. So then T is an automorphism. Okay, so yeah, so next example, We consider automorphism of so from Zn to Zn also there are how many automorphisms? P of n. So this is another example which are asked, which is asked in NET exam, and for problem solving also that is useful. Okay, so as another example, we consider the automorphisms of infinite cyclic group. This was finite cyclic group of order R. Now we consider automorphism of infinite cyclic group. So consider example number 2, which I leave as exercise. Again, very easy, not like this. So example 2, determine automorphisms of an infinite cyclic group. Right, so determine automorphisms of an infinite cyclic group, and this also is left as exercise. There will be only 2 automorphisms, and if you cannot solve this, then you can just refer the book by Husting. It is already given in the book by Husting. You can check that also.
Okay, so now uh, we prove an important result, which is Cayley's theorem. So before that, we define, just like inner automorphism, we define um, some map. It's very similar to inner automorphism. So let G be a group, and G is a fixed element. Suppose G is fixed element, then use based on this fixed element, define tau G from G to G by tau G of x equals to Gx for all x in G. So define like this, then we verify that this is not automorphism. This is not homomorphism, but what is tau G for each G. So for each G, we are defining tau G. So this is it is 1 1 and 1 2. So this is 1 1 and 1 2, and so this set tau G. Then I leave for you to check. You already checked this in the Google Meet. So this set tau G such that G belongs to G. This is subset of AG. AG means, so that means what? That means check that tau G belongs to AG for all G in G. So group G, and we take an element G, and then we are defining inner automorphism Tg of x equals to Gxg inverse. This is very similar, but this will not be automorphism. This will not be a homomorphism, but for all G, but it will be 1 1 and 1 2. So this is, so in other words, tau G is 1 1 and on 2. So tau G is 1 1 and on 2. And now we state Cayley's theorem, which says that every group is isomorphic to. So this is due to Cayley. It says that every group is isomorphic to a subgroup of AS for some set S. Every group is isomorphic to a subgroup of AS for some set S. So this is a very important theorem by Cayley. So what it says, you take a group G, and there is a 1 1 and 1 2 function. So you take one element here, then we have 1 1 and 1 2 function. So if we take G, we have tau G. If you take H, we have tau H. Right? So for every element there is an, and you operate here GH. Here you have tau G composition tau H. So this is what it says, that every group is isomorphic to a subgroup of AS. AS is set of all bijective functions from S to S for some set S. And we prove this result for by taking, we prove this result by taking S equals to G. So instead of taking any set S, we take S equals to G itself. So we prove this result by taking S equals to G. So we prove that, so let G be a group. So G is our group, and we prove this result by taking S equals to G. That means we prove that G is isomorphic to a subgroup of AG, not AS, AG. So this is first, what is that subgroup? So we first define that this set, whatever. So this is our first claim, that tau G for G in G is subset of AG. So that means we show it is 1, 1 and 1, 2. So which I have left for you to check here. But I think let me, or I can leave this as for you as exercise. There is very simple. Tau G, you can check that this is 1, 1 and 1, 2. So this is the first claim. So then, so we have a group G here, and you have this AG, and then we have, this is the set tau G, G in G. So we show that this G is isomorphic to this thing, subgroup of this. So we define a map. So define so for every element G, we have an element here tau G. So if I take any G here, so what I get here is an element tau G, which is 1, 1 and 1, 2. So tau G is in AG, right? So define psi from G to AG by psi of G. So any element G I take, then psi of G, I need one element of AG. That means 1, 1 and 1, 2 functions from G to G. So this is the 1, 1 and 1, 2 function. This is what we have defined, tau G. So define psi of G equals to tau G for G in G. Then what we claim is psi is a isomorphism. So if we show that psi is an isomorphism, then G is isomorphic to a subgroup of AG. Why subgroup I am saying? Because it is isomorphic to a subset of AG. Because we are not showing onto, we are showing just 1, 1 and homomorphism. That means G is not isomorphic to AG. To show that G is isomorphic to AG, we need 1, 1 and 1, 2 and homomorphism. We are not showing onto. So it may not be the full AG. It is never the full AG. It is isomorphic to a subgroup of AG. So first is the claim is psi is a homomorphism. So what we have to show? We have to show that psi of GH, this equals to psi G, psi H for all psi G, psi H for all GH in G. Right. So that is to show what is psi GH. Psi GH is tau GH. This is equals to tau G composition. So this is a composition between functions, as we know. The map is composition. So what we have to show is tau GH equals to tau G, tau H for all GH in G. So when what do we mean by this two maps are equal? So that means for every x in G, for every x in the domain, so tau G is a map from G to G, tau H is also a map from G to G. So for every x in the domain, we have to show that these two functions are equal. So tau GH of so tau G suffix H of x equals to GHX by definition equals to GHX. And on the other hand, what is, so this is RHS. So then on the other hand, what is left hand side? Left hand side is tau G. This is composition actually. We are writing. We are not just writing like this. Tau G O tau H, but we are just writing tau G tau H. It is understood that when what we mean is the operation is the composition between these two functions. So on the other hand, this is what? This is tau G of tau H of x. What is tau H of x? This is how it is defined. So tau G of x is gx. For every element, this fixed g, every element we multiply by g. So tau H of x equals to, this is tau G as it is, tau H of x is hx, and then apply tau G on hx. So applying tau G on hx, we have g hx, which is again GHX. So left hand side equals to right hand side. So that is thus tau GH equals to, so this equals to tau G composition tau H at x for all x in G. So then these two maps are equal. So this is done and then this is also done. Right? So this is homomorphism, and now finally we show it is 1-1. Then we are done. This proof is very easy, Cayley's theorem. Every group is isomorphic to a subgroup of AS for some S. So first step is we say that we take S equals to G itself. So every group G is isomorphic to a subgroup of AG. And so what is that subgroup? That is tau G. So for every G, you have a map, 1-1-1-2 map, G to G, that is tau G. So that is a map. And define that map as psi. Show that psi is homomorphism and show that it is 1-1. So it is isomorphism. That's it. So the next claim, psi is 1-1. So that is psi becomes an isomorphism. So to show that psi is 1-1, what do we have to show? Suppose either you can show that kernel of psi is singleton identity. That is also fine, equally good. What I am showing is psi G equals to psi H for some GH in G. Then I have to show that G equals to H. So this implies what? This implies psi G is what? Tau G equals to tau H for some. So tau G equals to tau H. This means what? These two functions are equal. So when the functions are equal, they are same on all elements. So the value is tau G of x equals to tau H of x. And this is for all x in G. Right? For all elements in the domain, these are equal. But how tau G is defined? Tau G is defined as Gx and tau H is defined as Hx. Again, this is true for all x in G. So this gives us, I can write G equals to H. Why? Because G is a group, and that means I am taking x equals to identity. If I take x equals to identity, what it becomes? Ge equals to He, so G equals to H. This is true for all x because these functions are equal. So tau G of x equals to tau H of x for all x. In particular, I can take x equals to identity, then I have G equals to H. So this is 1-1. So what we have shown is every group is isomorphic to a subgroup of AG. So Cayley's theorem is done. And now instead of this group, we can consider this such a map on a coset. Right? So this is the next lemma, let us call it lemma. So instead of group, the same technique, but now we are defining that on the coset. So this is the lemma which I am writing the statement. Again, this is very simple computation. So it's just an exercise. So let G be a group and H be a subgroup of G. So G be a group and H be a subgroup of G. Consider the set. Now we are considering the set of all left cosets. Consider the set of all. Instead of group, we are considering left cosets. So consider the set of all left cosets of H in G. And the set S equals to, this is the set of all left cosets, so XH, such that X belongs to G. Now instead of tau G, we define TG. Tau G was operating on G. Now this TG will be operating on this coset. So it will be operating. So for each G in G, just like tau G, we define. So define, not tau G this time, define TG from S to S, not G to G. वो ग्रुप में डिफाइन हुआ था. This is defined on the set S to S, which is set of all cosets by. So TG S, so XH equals to GXH. So let me write here. So defined by TG, an element of S. An element of S is nothing but it is left coset. So XH. See, tau G was defined as tau G of X equals to GX. The same. This is nothing but not GX but GXH. So it is another coset which is GXH for all XH in S. It's very simple. So similar result. Then, and instead of psi from G to AG, so we define psi. So define, instead of psi, we define theta from G to AS. See, that was G to AG. So because tau G was from G to G, here TG is from S to S. So define theta from G to AS by, see why do we define this map? For every element we have a function S to S, 1, 1 and 1, 2. So AS, for every element G, we have a function in AS, 1, 1 and 1, 2 function. So every element there is a function. So naturally theta is a map defined from group to this. This is defined by theta of, how do we define? You can easily find it out. No need to think also. This is very natural function. For every G, there is a function in AS. What is the function? That is TG. So this is defined by, for all G in G. So this is how it is defined. So this much is given, the statement. Now what we are proving. So then this is what we have to prove. This is all what we have to prove. Then theta is a homomorphism. This is the first thing. And kernel of theta is the largest subgroup, is the largest normal subgroup kernel of theta is the largest normal subgroup of G contained in H. Kernel of theta is the largest normal subgroup of G contained in H. So I'm again repeating the statement. The statement is, you can break all this in different parts in exercise. So just as tau G was defined earlier, that was from G to G, tau G of X, for every G, we have a map tau G of X equals to Gx. Here we define TG, not tau G, but not from G to G, from cosets. So for coset we need a subgroup. So what we are starting, G is a group, H is a subgroup. And S is the set of all left coset of H in G. And define TG from, for every G, tau G from G to G. No, this is TG from S to S. TG of tau G of X equals to Gx. So TG of not X, but it is coset. So XH. it equals to gxh. Just very, very, very similar. You see, if you compare the proof. And then we had map psi in Cayley's theorem. Psi from um, G to AG. So here psi from G to AS. And that is natural defined. Why? Because you take an element G here, then for corresponding to that G, we have one and one two function. So obviously, this is the map we have to define. Theta, which maps G to the one and one two function here. Right? So that is this is defined. So this much is given. This is where it starts what we have to prove. Then theta is a homomorphism. Kernel of theta is a normal subgroup of G. Kernel of theta is the largest normal subgroup of G. Kernel of theta is contained in this subgroup H. So these are the things which we have to prove. So let me list all the things what we have to prove. First of all, to show this map, first of all we have to show that this guy TG is in AS. So this is the first thing which we have to show. So first thing, if I write here, first thing we have to show that this TG belongs to AS for all G in G. This is the first thing. This element here, this is in AS because this is how the map theta we are defining, G to this. So TG is in AS. This is the first and foremost thing which we are showing. Second is this theta is a homomorphism. This is the third one. Kernel of theta is a normal subgroup of G. So this is the third one. This is the fourth one. Largest normal subgroup. This is the fourth. So this is the fourth one, largest normal subgroup. And finally, kernel of theta is, or you can show that kernel of theta is contained in H also. That is, so this can be considered as fourth one. And then largest, finally, it is the largest subgroup of normal subgroup of G, which is contained in H. So these are all 4-5 exercises, which we'll do. I'll not give this as exercise, don't worry. So first we show that TG is in AS. So this is our first claim. So TG belongs to AS for every G in G. Right, so this is the first claim. So we show that TG is 1 and 1 2. So for fixed G, for fixed G in G, how TG is defined? So TG of X equals to G of XH. Sorry, TG of it is XH equals to GXH. Right. So this is a mapping from this TG is a mapping from S to S. You are taking a coset. S is the set of all cosets, left cosets. So we are taking a coset XH, and where TG maps GXH. So G is also an element of GX is also an element of G. So this is also left coset GXH. So TG is a map from S to S. Now for any for two elements XH and YH, I am taking two elements in S. Suppose TG of XH equals to TG of YH for some XH and YH in AS. So this means what? GXH equals to GYH. So these two cosets are same. So if I multiply by G inverse on both sides, I have XH equals to YH. So this implies that T is not this T, but this TG is 1 to 1. Right? So I have shown that it is 1 1 1. Now for in AS, I have also to show that I am supposed to show that it is onto. So what do we do for onto? We take any element in the codomain. So S, what is S? S is a set of all left cosets. So take some left coset. So for showing onto, let YH belongs to S. And how do we show that this is onto? So this is always I tell In the class also I tell, last video also, last video I told this. So what we do is we assume that it is onto, and then do the back calculation. So how do we do the back calculation? Suppose there is XH. There is TG is from S to H. So suppose there is XH which goes to YH, which we have assumed. So we have assumed YH in the codomain, and we have to find something which is mapped to YH. So this is what we have to find. So suppose there is already an element XH we have found. So how XH will look like? So TG of XH equals to this YH. Agar onto hai, so we will find some XH. Then now we will determine what this XH looks like. So this implies G of XH equals to YH. So this implies GXH equals to YH. So what is XH? We have to determine what is XH, right? ये XH कैसा होगा? So what is XH? XH equals to G inverse YH. That's it. We have got. On to मान के चलो, and then whatever that this domain का element, whatever we find out, that is our magic element. So we start with an element in the codomain. So let YH belongs to S. Then we can say that G inverse Y, this is our magic element. G inverse YH. This is also a coset. G inverse multiply कर दे दो left side में. So G inverse Y, that is also left coset. That also belongs to H. And what is TG of G inverse Y? G inverse YH. This is nothing but G of G inverse YH. So G of G inverse YH, which is nothing but G inverse YH, which is YH, and that is where we started, YH. YH से start करो, we got YH, so that means this is onto. So how do we get this element? We start believing that it is onto, and suppose there is an element in the domain, then what it will look like this. So when we write this element here, we don't all of a sudden feel that some magic has happened. How did we get this element? So always back calculation, then we remove all the back calculation, so we don't have to remember the proof. This is the technique to approach, right? So thus TG is onto, and hence I can say that our claim, so that means TG belongs to AS. So it's 1, 1 and onto functions, 1, 1 and onto functions. So our first claim is done. So this is what we have proved. And now our second claim, the theta is a homomorphism. So theta is defined as theta from G to AS. Theta of G is this map TG. We have to show that this is a homomorphism. So that is our second claim. Theta is a homomorphism. So to show that theta is homomorphism, so we start with let G and K, this be in G, and to show that theta is homomorphism, we have to show that theta of GK equals to theta of G, theta of K. So that is to show that so this means theta of GK means what? This is not tau, this is TGK equals to TG TK. Just like in above case, this is what we have to show. So to show that this TG TK, can you show this? So these two maps are equal, that means that is to show that TG, so TGK at domain. What is the domain? All this TG, TK, all these are functions from S to S. These are functions from S to S. So domain is left coset. So for every left coset, they are equal. So this is same as TG composition tk at xh. So again, just like previous case, what is left hand side? Left hand side is tgk of xh. This is nothing but gk of xh, which is nothing but gkxh. So this is the left coset. And on the other hand, right hand side is tg tk of xh. This is by composition. This is tg tk of xh. And what is, so this is tg, what is tk of xh? That is kxh. And again, what is tg of kxh? So this is gkxh. So left hand side equals to right hand side. So we are done. So theta is homomorphism. So that means thus tgk, this is what we have obtained. This is tg th, which is composition of tg composition th. So this is true because for all xh in S, right? So this is, we have to show that this is true for all xh in S. So these two maps are equal, and hence theta is homomorphism. So hence theta is a homomorphism. Right. So what was the next plan? So first thing, we have shown that tg is 1 1 and 1 2. So that thing we are done. Next thing is theta is homomorphism. So that also we are through. Second one also we have done. What is where is the third one? Third one, yes, kernel of theta is a normal subgroup of G. Now kernel of a homomorphism is always a normal subgroup. So we can state this here. That exercise also you have done. If you have not done, it's an again good exercise to. So claim 3, since kernel of a homomorphism, if you have not done this exercise, then it's a good time to verify this. Since kernel of a group homomorphism or a homomorphism so kernel of homomorphism is a normal subgroup. We can say that kernel of theta is normal in G. So that means kernel of theta is a normal subgroup of G. So that part easily follows from the fact that kernel is. So this part, third one, this is also done. Kernel of theta is it's a normal subgroup of G. So now the fourth one, that kernel of theta is contained in H. So that is, see, all these are very trivial exercises. So we claim that kernel of theta, this is subset of H. So when we want to show that this is subset of this, so we start with one element here. So let G belongs to kernel of theta. So this means then theta G is identity. What is identity? What is theta? So theta is a map from G to AS, and theta of G, it is defined as this TG. So identity is the identity map here in AS. So we denote it by I. So theta of G equals to I. So this implies, so that is theta G equals to I means TG. Theta G is defined as TG equals to I. So this means and so TG of XH. So this is a map from S to S. So this is I of XH, which is nothing but XH. Identity of XH is XH. But then what is TG of XH? TG of XH is GXH. This is of course, this is true for all XH in S, for all elements, all left cosets in the domain. So then GXH, because TG of XH is GXH, gxh equals to xh, right? So gxh equals to xh. Uh, we have to show that G belongs to H. So this is true for, as here we have written, for all XH in S. So I can take, instead of XH, I can take as, this implies GEH equals to EH. So this implies GH equals to H. So in particular taking, this is true for all left coset XH in S. So in particular taking XH equals to, I take EH. This is also left coset. So GH, so this implies that G belongs to H. If the coset GH equals to H, then G belongs to H. So we started with G belongs to kernel of theta, and what we have got is G belongs to H. So see, this one you cannot see it from the straightforward, but when you start doing it, just using definition, you get this. So whatever we claim is done. So then thus kernel of theta is contained in H. So one more thing which we have proved is kernel of theta is contained in H. It is normal subgroup of G, that is all. Now it is the largest normal subgroup of G contained in H. So last one, kernel of theta is the largest normal subgroup of G contained in H. So how do we show that it is the largest? Suppose N is a normal subgroup of G, N is contained in H, then N is smaller than kernel of theta. That means N is also subset of kernel of theta. So this is the final claim. Kernel of theta is largest normal subgroup of G contained in H. So this is for this claim. So we assume that so suppose N is a normal subgroup of G contained in H. So suppose N is a normal subgroup of G. Such that N is contained in H. Then we show that N is contained. So N is contained in kernel of theta. If we show this, then we are done. N is subset of kernel of theta. So N is any arbitrary normal subgroup of G which is contained in H. So if we show that N is contained in kernel of theta, then we are done. Right? So this is a bit tricky, not difficult, but this is a bit tricky. So we have to show that N is subset of kernel of theta. So let N belongs to N. Since N is normal in G, N is normal in G, by definition of normal, X inverse Nx belongs to N for all N in N and for all X in G. Gx, G and G inverse. So for all X in G, this belongs to N. And this is subset of H. This is what we have assumed. N is a normal subgroup and N is contained in H. Then kernel is one of this largest. So N is subset of H. So X inverse belongs to H. So that is Xn. So X inverse Xn belongs to H. X inverse Xn belongs to H. Okay. That means what? So that means this coset X inverse Nx H equals to H. So this implies this. And so if I multiply by X both sides, so this is Nxh equals to Xh. Of course, for all X in G here. Right? So if it is for all x in G, here also for all x in G, and so here I can say that this is for all xh in S, because this is same as for all x in G, for all x in G. So this is same. If whenever I take x in G, I have xh in S. So this is true for all xh. But what is nxh? So nxh is nothing but this is T of n, T of Tn of xh. This is nxh. This is same as, but xh is same as identity ixh, ixh for all xh in S in the domain. Right? So this means for every element, for every left coset in the domain, they are equal. So that means Tn equals to I. So Tn equals to I. Uh, that means what is Tn? Tn is nothing but theta of n. Theta of n equals to I. So that means n belongs to kernel of theta. Right? Again, this is done by back calculation, so it is very easy. Why do we take this element? So n is suppose n is a normal subgroup of G, n is subset of H. Then what we show that n is subset of kernel of theta. That means kernel of theta is largest such normal subgroup of G contained in H. So we start with any element in n. We show that so we start with n in n. So this is where we start, and then what we show finally, n belongs to kernel of theta. So then n is subset of kernel of theta. So this implies, so thus n is a subset of kernel of theta. So for that, because it is normal, so x inverse nx is in n, but n is contained in H for every n in n and for x in G. So x inverse nx is contained in H. Now we have got for all x in G. So if I take the coset, then this is in H, so that this coset by x inverse nxh, this is nothing but EH, which is same as H. And so if I multiply by x, so I have nxh equals to xh. But now for all x in G, so for all x in G, what is xh? Xh is a left coset. So I can say equivalently, I can say this is for all x, for all xh in S, for all left coset xh in S. But nxh, this is nothing but Tn of xh. This is how Tn is defined. Tg of xh equals to gxh. So Tn of xh equals to nxh. So this is Tn xh, and this is xh is identity function. So that means for all left cosets in the domain, this is equal. So for all xh in S, they are equal. That means these two functions are equal on S. So Tn equals to identity. But what is Tn? Theta of n. Theta of G is Tg. So this is theta of n is identity. That means n belongs to kernel. So we had, right. So this is the lemma, and what is important is a corollary of this. But I think it is already, I think, more than an hour maybe. I don't know when I started recording this, but just go through this result, and then we'll recall the result and start with the corollary in the next video.